Hello everyone. In this lecture, we will discuss about computer system architecture, and our prime focus is on the memory hierarchy. What is the role of memory or storage in the computer system architecture? So you can see in this figure here, there are basically three components are there when we talk about a computer system architecture. So for any computer, you have processor, then main memory, and the IO. These are three components which are interconnected, and the interconnection structure is the buses. So buses are divided into three parts: addresses, in the lines in which address pass for the source and destination, and the control lines, the commands for the moving the commands, and the data. So these buses becomes the medium for the transferring the data from one component to another component. So here we can see the processor requires the data to process the data, and that data is either available in the main memory or the data is coming from the IO. So IO, all the secondary storage devices which are connected through the input-output system. So if you expand this architecture, so from the single computer to, let's say, for a system for the large organization, or even for a small organization also, if we the entire IT infrastructure, if you look at this IT infrastructure, can be divided into three parts, and these three parts are the computing, networking, and storage. If you just see the three-tier architecture. So computing involves the different applications like web servers, video conferencing, data server, and the streaming applications, and there can be a lot more other applications can be there. Networking, which provides the connectivity between the computing nodes. Say for example, a web service running on a computing node that talks to the database service running on another computer. And the third and the important part, which is important with respect to this particular course, is the storage. And there are two types of storage. One is a persistent, other is a non-persistent storage. And storage is a place where all the data resides, whether it's computational data, which we call as a non-persistent data, and the non-computational data means that is not required immediately but may be required at a later time. So both type of storage is involved in that. So these are the basically three layers or three-tier architecture in general present. Now we want to see that how the memory requirement of the processor, how the processor requires the memory. So processor requires the memory in two ways. One is the data which is required per computation data, means that at the particular point of time the data is required, and other is a permanent data which is stored in the secondary storage, or which is called as a persistent data. So if we separate so there is a separate memory storage required for both type of persistent and non-persistent. So from the technology point of view, we can divide this. So it can so from the technology point of view, it is volatile memory versus non-volatile memory. So the per computation data which is required, that is a volatile memory, and the persistent data, that is non-volatile. Similarly, cost wise, if you look at, then the computation data, because the processor needs it is nearest to the processor in the system architecture, so it should be faster, and if it is faster, then definitely it's a costlier as well. So that is, the per computation data is a faster and costlier, and the persistent data, and that typically we call as a storage. So that is compared to the non-persistent data or the per computation data, it is slower and the cheaper. So I say persistent is a slower and cheaper. So this is this way it is the processor requirement is there. So processor essentially for the computation, essentially we require both data. Now from this example, we'll try to understand the bandwidth requirement, memory bandwidth requirement for the processor. So for this, I took example of the different machines. So here I have a machines which used in 80s and then 90s and then 2000 and around 2008. So the different class of machines in terms of the capability wise, so pipeline processor, superscalar pipeline processors, and then hyper-threaded and multi-core processors. So depends. So what is the difference between these different type of processors in terms of the clock cycle? Their clock cycle is, as we are progressing, the clock cycle is reducing. So per clock cycle, the amount of time, so cycle time is reducing. Cycle time reducing means the processor becomes more powerful or faster compared to the number of operations which it can perform. So instructions, number of instructions per cycle, this is also changing with respect to the number of machines as shown here. So our interest is here to calculate the instructions per second, how many instructions per second. So if you just multiply these two values, clock cycle and the instruction per cycle, so cycles per second and the instruction per cycle, then I will get the instructions per second. And you can see the instructions per second value which I am getting, the maximum is for the hyper-threaded multi-core processors. Now this instruction per second and the instruction size, if you multiply these two and instruction per second is available, instruction size is available, and the operands in the memory per instruction is required. So ultimately what I want to calculate, the bandwidth demand. So bandwidth demand calculation will be number of instructions per second multiply with the instruction size plus the operand size. So the amount of data per second which is processor needs it or processor wants can process at that point of time. So the bandwidth demand is, if we calculate this value, then for the machines, the DACVAX machine which is came in 1980s, the bandwidth requirement is 4.4 Mbps, and this is increasing as we are moving towards the hyper-threaded or multi-core processors. So it becomes 100 Gbps, 100 gigabit per second. So we can see here, this is the way the processor speed is increasing, and at that speed the memory or the data should be provided to the processor. If the data is not, we are not able to provide the data at that rate to the processor, means we are not able to utilize the processor's capability. So that's a big challenge. So and this is with respect to a single machine. If you have I have a multiple machines, and then in that case this requirement, further bandwidth requirement is further increasing. So this is the biggest challenge that we need to address as an storage or the memory part. So now the question is, how do we meet the memory bandwidth requirement? So one of the observation came from by running the different programs is a typical data item is accessed more than once, means multiple time data, same data or a set of data is accessed, and this we call as a locality of reference. So in every program the locality of reference can vary, means the amount of data which requires processor access that data frequently. Same set of data it is accessing frequently. So there are two types of locality of reference. One is called as a spatial locality. So spatial locality, and other is temporal locality. So there are two type of locality. So spatial locality means, suppose for example a data is stored in a list of items are there which are stored in an array data structure. So that data is stored in consecutive memory location in sequence, starting from one location to going in a sequence. So that's the example of spatial locality. And similarly for the temporal locality, from the programming point of view, the example is you have loop structures in most of the programming, or almost all programming languages have the loop structure. So the statements which belongs to the loop, they are executing multiple times, depends upon how many iterations of that loop is executing. So that's an example of temporal locality. In both the cases, the what is common is that some set of data is accessed frequently again and again, and this can be leveraged to organize our memory in such a way that we can keep this data. If you know that at this particular point of time for the next let's say few amount of time, the data process is going to access this data through the locality of reference, we come to know, and that data we can keep in some high speed memory. We don't have to put entire program data into the high speed memory. We just keep this small amount of data based on the locality of reference on high speed memory, and we can provide the data to the processor at a higher rate. So that will meet the memory bandwidth requirement, keeping the cost in the cost of the entire memory is also is in a reduced. So if we keep the entire data in the faster memory, costly memory, then definitely overall cost will increase, and that will not be a feasible solution. So the one of the observation which came from this locality of reference concept is to meet the processor bandwidth requirement, the multiple levels can be introduced. So I can say that I have some memory in my processor which is access time is very low, means it's a faster memory. So in fast memory I can keep the data which is processor needs frequently, and what data processor requires frequently, that's changing with respect to time, but through the locality of reference I come to know that okay, now this data is going to be required, so that data can be provided at a faster rate. So there's notion of the multiple levels of the memory, not only a single level of memory should not be there. So earlier days, how this multiple level of memory came into the picture. So register set is the closest to the processor, and then the primary memory, then secondary memory, and then the archival. In present day, how this multiple levels has been changed. So again the register set is there, then the multiple levels of cache memory has been introduced. So here it is L1, L2 cache, and nowadays even the systems have the up to the L3 caches are there, L1, L2, L3. So 3 levels of cache memory are there between the processor and the primary memory. So then you have, after cache levels, you have the primary memory and then direct attached storage that is formed in the disk, and the next layer is introduced in the storage is that is a networked storage, which is network wide available. So more details we will do in the subsequent lectures about the network storage, and finally the archival storage, that is the tape drive is used for this, that is just offline data storage. So what is the motivation behind this multiple level memory system is that to amortization of the cost, and as we move down, so in this hierarchy, if you look at in this hierarchy from processor to go to the archival storage, this hierarchy, in this hierarchy top to bottom if I move, then cost is decreasing and the cost is decreasing and the speed is also decreasing. So there are some property of the multi-level memory hierarchy. That one of the principle is that called as an inclusion principle, means if you have a 2-level memory, suppose you have 3-level memories there, let's say, so highest level is H, then you have H plus 1 and H plus 2. H is the closest to the processor, and H plus, as you move from H to H plus 1, means it is away from the processor. Away from the processor means a slower memory, its size is large, H plus 1 have the larger size than H. So the idea is that okay, the data which is available at level H, that data is also available at H plus 1 as well as available at H plus 2. Similarly, similar kind of relationship is between H plus 1 and H plus 2 as well. So how we how we can take advantage of this? So we know that okay, the processor is accessing the data. So processor is accessing the data from the level H, that highest level, and if so H level I cannot provide the entire set of data which is processor required, that keep changing with respect to the time. So whenever the new data is requested by the processor which is not available at the highest level or the closest level, then the data has to be moved from the next level to this level. So at that time it may be possible that okay, the previously whatever data has been fetched or put into the H level, that data might have changed because during the computation operation that data might have overwritten. So this overwritten data needs to be copied back to the H plus 7 to make the consistency data, otherwise data will become inconsistency if I am not writing back. But if no data has been changed, then I don't need not to copy the data at level H to the H plus 1. Just new data can be replaced if no data has been changed. So that advantage can be taken because writing back and then reading, so writing back again, writing is a costly affair. So it requires increased further latency to access the new set of data. So this can be a good saving in that case. Now if you just quickly look at that, okay, the effective access time for the two level memory hierarchy. So suppose I have the two levels, one is H and other is H plus 1, and the access time for H is TH, and for the H plus 1 level access time is TH plus 1. If the data is not available in H level memory, then H plus 1 data is to be accessed from H plus 1. So for that the time is H plus 1. So if I calculate the effective time, so which I am calling as a T effective in a two level memory system, and also I need to consider here what is the miss penalty at H level. So let's say H level as a miss penalty, the amount of data which is miss is P miss, probability of data to be miss. Means suppose 100 data requests come, out of 100 P miss will be the data which not be available. So 1 minus P miss will be data can be accessed from the level H. So if I'm interested in calculate the effective time. So if I say that data which is available, the access time for highest H level is TH, and how much data is accessed, 1 minus P miss is accessed at the H level, and the remaining data, that is P miss data, the data which is not available in H level, that data, for that data latency is TH plus 1, and this H plus 1 includes the access time of H plus the overhead which is overhead requires to access the data from the next level. So it includes both the times, right? So in this way I can calculate the the effective time. So this effective time will be definitely in between the TH and TH plus 1, somewhere in between the TH and TH plus 1. So how closer it is so our requirement is it should be closer to the TH. That's the place where the effective your locality of reference concept is used. So most of the data should be available at the highest level of the memory. So if it is more than 90%, that is always preferable. If it is less than 90% coming, then it is always your effective time is going towards the TH plus 1. So now using this formula, if I calculate the memory efficiency, so memory efficiency is 100 multiplied by the TH divided by T effective time. Effective time we calculated in the previous slide. So if I just replace this the ratio of the access time of two memory levels, TH plus 1 divided by TH with R, then this memory efficiency can be written as 100 divided by 1 plus P miss into R minus 1. So now my R is the parameter which tells me that how the maximum memory efficiency I can relate with that. So if R equals to 1, then I can get the maximum memory efficiency, that is 100%, or the P miss equals to 0. So for the different levels of the memory, like CPU and the SRAM. So CPU SRAM is basically cache memory, and the CPU means the data is available in registers at itself. The R is 10 times, means the SRAM is a 10 times slower than the CPU or the memory which is there in the CPU, this is registers. Similarly, between main memory and the CPU speed mismatch is, so assuming that okay, CPU can access the data, means data which is available in the CPU register set, that is the unit of time is 1 unit time is required. So the ratio coming here is 50. So as we move from CPU to in the memory hierarchy away from the CPU, you can see that this R is increasing, means the latency is increasing. So if we talk in terms of the memory technologies, then the computational memory technology is basically the cache between the CPU registers and the main memory, which is static RAM is used, and access time, typical access time for this memory is a 10 nanosecond. Then the next computational memory in the memory hierarchy is a main memory. Main memory is called as a dynamic memory. Why it is called dynamic memory? Because there is a component capacitor is there. So it is one cell of the dynamic RAM is one transistor and one capacitor. So the due to the capacitor, because capacitor charge leak as with respect to the time, so it requires some refreshed circuitry. Periodically refreshing is required. That's why it's called as a dynamic. So typical access time for this is 50 nanosecond, and refresh cycle is 100 millisecond. Now come to the persistent part, or the typically we call as a storage storage data used for the storage part. The memory technology for this is a hard disk we use, and the flash drives, which is coming up recently. So hard disk used for the persistent online storage, typically access time is 10 to 15 millisecond. You can see that the difference between the DRAM and SRAM, how slow that hard disk is there. And it is a semi-random. It is not completely random and completely sequential, because the data is accessed in terms of the blocks, and typical block size is 512 bytes. The cost is, it is very cheaper compared to the DRAM and SRAM. And solid state drives are basically, it's a form of a electrically erasable programmable ROM, so EEPROM basically, and it's used for persistent online storage. Number of erases which are limited, or currently as per the current technology, somewhere near 100,000 to 500,000, depends upon vendor to vendor. And read access time also, it depends upon how the memory has been constructed. Read access time is 50 nanosecond, which is very, so compared to, because this is a replacement of hard disk, and you can see that hard disk access time is around 10 to 15 millisecond, and this access time is 50 nanosecond, and it's quite near to the main memory. So this is a fast memory compared to the disk. And write access time, so read access time is a fast, but write access time is a 10 microsecond, so that is slightly heavy because of this the programming, it requires erasing and then writing. So due to that, its latency is more in terms of the writing. It is again semi-random, so block level data is reading or writing, and cost is higher side compared to the hard disk. Then for archival purpose, the memory technology which is used, the magnetic tapes. Tapes are very cheaper in, but they cannot be used for the online data. It can be used only for the offline or archival backup purpose only. And this is the one of, since long time, magnetic tapes are used for the archival purpose, and data access is sequential here. So we have seen that, okay, caching is something that is a very common principle used everywhere. So one of the caching is the level 1, level 2, level 3 caches that between RAM and the processor, and at the different places. So between, so let's say the L1 is placed on the processor chip itself, so its R is basically 1 to 2 only with respect to the processor, because it's very near to the processor, and the SRAM are used for that. Static random access memory, and L3 is typically on board, that's on the processor or motherboard is there, and R is the ratio between the processor access time and the L3 memory access time, that is 5 to 10. So caching is basically generic. It is not like that, okay, only we say the cache memory is only the memory which sits between the main memory and the processor. Caching is a general phenomena, and say for example even disk cache, so any the caching can be used between any two parts of the memory. So in a memory hierarchy, between any two levels the caching can be used, like the caching is used between main memory and the processor. Similarly, it can be used for the main memory and the disk, between the disk secondary storage, the direct attached storage to the system. So that is called as a disk cache. So what is the advantage of the disk cache is there, if the data is the processor requested data is available in the disk cache itself, then the data reading is not required from the actually from the physical device disk, and the lot of latency can be reduced in terms of seek time and rotational. The mechanical component of the disk is there, due to that more latency is there, that's why the disks are slower. So that can be avoided if the data can be provided from the disk cache itself, that is available in the disk controller. So, and this cache is usually, it's a semiconductor memory as compared to the the magnetic memory which is there in the disk. Magnetic memory access time is more compared to the semiconductor memory. And so this is the one. So the caching is a principle which is used to improve the latency or memory access time, such that we can meet the processor requirement of the memory bandwidth requirement of the processor can be met. But this partially solves the problem. Caching cannot solve the entire problem in terms of meeting the memory bandwidth requirement. So we need further more you can say efforts in terms of organizing the data or the different storage concepts we need to use to meet this ever growing memory bandwidth requirement of the processor. So thank you very much.